Have you ever woken from a dream so real, so incredibly vivid, that the lines between the sleeping world and waking life blurred into almost nothing? A dream that lingered, clinging to the edges of your consciousness long after you opened your eyes? A dream so convincing you questioned which world was true, which version of reality held more weight, more authenticity? Was it the world you knew, or the one you just left behind? This uncertainty, this fundamental questioning of what is real, has haunted humanity for millennia. It's a thread woven through our philosophies, our art, and our very understanding of existence. Consider Zhuangzi, the ancient Chinese philosopher, dreamt he was a butterfly. Upon waking, he wondered, was he Zhuangzi dreaming of being a butterfly, lost in the illusion of flight and freedom? Or was he in fact a butterfly dreaming of being Zhuangzi, a fleeting creature imagining a life of complex thought and philosophical inquiry? Plato's allegory of the cave asked if we mistake shadows for reality, mistaking the fleeting projections on the wall for the true forms that cast them, suggesting our senses might only reveal a fraction of the truth, a distorted glimpse of a larger, more complex reality beyond our immediate perception. Centuries later, Descartes imagined an evil demon deceiving him, a powerful entity dedicated to distorting his perceptions and manipulating his senses, making him doubt everything, even the existence of the world itself, the very ground beneath his feet, the air he breathed, all potentially part of an elaborate deception. These stories, Zhuangzi's dream, Plato's cave, Descartes' demon, are the philosophical ancestors of today's simulation hypothesis, the idea that our reality might be a computer-generated illusion. They all ask, can we truly trust our reality, the evidence presented by our senses, the world as we perceive it? Or are we experiencing a filtered, possibly illusory world? A carefully constructed simulation designed to mimic reality, but ultimately something else entirely? As we build digital worlds increasingly sophisticated and immersive, this ancient question gains new urgency, a renewed relevance in the face of our technological advancements. Are we living inside the grandest computer program ever written? A simulation so complete, so seamless, that we are unable to distinguish it from what we consider to be real? The simulation hypothesis, once relegated to the realm of philosophical musings, leapt from philosophy to science in 2003. This marked a significant turning point as the concept began to be examined through a more rigorous analytical lens. This shift occurred when Nick Bostrom, a philosopher at the University of Oxford, introduced a statistical argument that shook academia and sparked widespread debate. His approach wasn't based on proving the simulation hypothesis, but rather on assessing its probability. Bostrom's argument centered around a trilemma, a proposition that one of three statements must be true. The first possibility he presented was that civilizations invariably go extinct before reaching technological maturity, before they develop the capacity to create detailed ancestor simulations. This suggests a grim outlook for any civilization, including our own. The second possibility is that even advanced civilizations capable of creating such simulations lose interest in ancestor simulations. Perhaps they find the process ethically questionable, technically unfeasible at scale, or simply prefer to dedicate their resources to other endeavors. The third, and perhaps most unsettling possibility, is that we are almost certainly living in a simulation. If consciousness can exist on computers, a concept increasingly explored in artificial intelligence research, then advanced civilizations could potentially create countless simulated worlds. These worlds could be indistinguishable from what we perceive as reality. Each of these simulated worlds could be filled with beings unaware of their artificial origins, living out lives within the confines of a meticulously crafted digital environment. They would experience the same range of emotions, sensations, and beliefs as we do. If most civilizations never reach this stage, due to self-destruction or a lack of interest, or actively choose not to simulate realities, then we are likely in base reality, the original, unsimulated universe. But if they do, and ancestor simulations become commonplace, The number of simulated beings would vastly outnumber real ones, potentially by orders of magnitude. Statistically, considering the sheer volume of potentially simulated beings, that would make it far more likely that we are ourselves simulated, rather than original inhabitants of base reality. Bostrom doesn't definitively claim we are in a simulation. He simply argues that, given these premises and the potential for a vast number of simulations, the odds are statistically not in our favor of being in base reality. The simulation hypothesis, therefore, is no longer just a thought experiment confined to late-night philosophical discussions. It's evolved into a statistical wager, a calculated gamble on the very nature of our existence. The central question has shifted from a speculative what-if scenario to a more quantifiable how likely is it? And that's a question with profound implications, one that the scientific community can't easily ignore as it grapples with the boundaries of reality and the potential for simulated universes. Physics, in its relentless pursuit of understanding the cosmos, has uncovered strange and unsettling truths. These discoveries, often emerging from the depths of quantum mechanics and cosmology, present a reality far stranger than we could have ever imagined. Some of these truths eerily echo the simulation idea, suggesting that what we perceive as reality might be a carefully constructed illusion. Could our universe be nothing more than lines of code in some grand cosmic program? In the bizarre world of quantum mechanics, reality seems to collapse into certainty only when observed. Before observation, particles exist in a superposition of states, a blurry haze of possibilities. This is like a video game, rendering only what the player sees, conserving computational power by not fully generating the unobserved world. The universe, in this view, is only defined when we look at it. The holographic principle takes this a step further, suggesting our seemingly three-dimensional universe could be a projection from two-dimensional information stored on a distant boundary. It's as if reality is a cosmic hologram, with all the information needed to describe our 3D world encoded on a 2D surface, much like a hologram stores a 3D image on a flat piece of film. The late John Wheeler, a renowned physicist, famously proposed it from bit. This profound idea suggests that information, not matter or energy, is the universe's true foundation. Everything we perceive, from the smallest particle to the largest galaxy, ultimately arises from bits of information. The Bekenstein bound, derived from black hole thermodynamics, sets a fundamental limit on how much information can be contained within a given region of space. This hints that reality, at its deepest level, is not infinitely detailed and continuous, but rather has a finite information capacity. It suggests that space itself might be pixelated at the smallest scales, like a digital image when you zoom in too far. Building on this idea, theories like loop quantum gravity suggest that space-time itself is not smooth and continuous, but is instead made of discrete fundamental units, the ultimate pixels of reality. If the universe is fundamentally composed of information, governed by informational laws, then it becomes plausible, even if unsettling, that our reality could be the output of a vast cosmic computation, running on a scale we can scarcely imagine. In this scenario, the laws of physics, the very rules that govern our existence, might be nothing more than the code, the elegant and intricate instructions of an unfathomably complex algorithm, constantly running and shaping the universe we experience. Digital physics proposes the universe is a vast computation. Konrad Zuse and later Stephen Wolfram argued that simple computational rules could generate the complexity we see in nature. Cellular automata, grids of simple rules, can create lifelike patterns, suggesting complexity can emerge from simplicity. Some physicists, like Gerard 't Hooft, explore whether quantum mechanics itself could arise from a deeper deterministic computation. The physical church Turing thesis posits that any physical process can be simulated by a computer. If true, our universe could be perfectly replicated within a powerful enough system. In this view, space and time are data structures, and the universe is mathematics and information in action. The line between real and simulated reality blurs. If we live in a simulation, could we find evidence? glitches, or digital artifacts in our universe. Physicists have searched for signs, like energy cutoffs in cosmic rays or asymmetries that might reveal a computational grid. So far, no such evidence has been found. If a grid exists, it's far beyond our current detection. James Gates Jr. discovered error-correcting codes and supersymmetry equations, reminiscent of digital technology, but this is not definitive proof. Simulating our universe down to the smallest scale would require more energy than the universe contains, making a brute force simulation seem impossible. Unless the simulators exist in a reality with different laws, the energy demands are staggering. The search for simulation artifacts continues, but the evidence remains elusive. For now, the seams in the fabric of reality are well hidden. The simulation hypothesis faces sharp criticism for being untestable and unnecessarily complex. Occam's razor favors simpler explanations. Adding unseen programmers and computers to explain a universe that already works is a stretch. Critics like Sabine Hossenfelder argue that without falsifiable predictions, the hypothesis is more pseudoscience than science. Bostrom's argument relies on huge, unproven assumptions about civilization, technology, and motivation. We have no empirical evidence, no glitches, no digital grid, no anomalies in the laws of physics. The universe appears smooth, continuous, and self-contained. Most scientists see the simulation hypothesis as an entertaining story, not a scientific necessity. Until we find real evidence, it remains a philosophical curiosity. Simulating every particle in the universe is wildly inefficient, so some propose a more plausible model, an on-demand, self-evolving simulation. Like a video game that generates details only as the player explores, the universe might render complexity only when observed. This approach would save immense computational resources, focusing only where needed. It also echoes the observer effect in quantum mechanics. Reality loads when we look. The fine-tuning of physical constants could result from cosmic evolution, not preset design. In this model, the universe is a program that writes and refines itself as it goes. The simulation, if it exists, is dynamic, efficient, and ever-evolving. The simulation debate is a tug-of-war between possibility and evidence. Proponents cite Bostrom's statistics, rapid tech progress, and the mathematical nature of physical laws as support. Hints like error-correcting codes and fine-tuned constants add intrigue, but not proof. Critics point to the total lack of direct evidence. No glitches, no digital artifacts, no need for a programmer. Occam's razor and energy constraints make a faithful simulation seem implausible. The hypothesis requires a vast, unproven superstructure to explain a universe that already explains itself. Without evidence, it's a solution in search of a problem. The simulation hypothesis remains intellectually stimulating, but unproven. So, are we living in a simulation? The idea is grand, but science demands testable, evidence-based theories. The simulation hypothesis is coherent, but lacks falsifiable predictions and empirical support. Arguments for it are philosophical. Arguments against it are grounded in observation and scientific reasoning. No artifacts, no glitches, and insurmountable energy requirements keep most scientists skeptical. For now, the universe appears to be a self-contained system governed by mathematical laws. The simulation hypothesis is a fascinating lens, but not a scientific necessity. Asking the question pushes us to examine reality more deeply. But the simplest conclusion is that our universe is the base reality. Until we find a glitch in the matrix, open-minded skepticism is the most rational stance.